Once again, welcome back channel. Very warm welcome back on my channel. So we will continue physics, and the topic is wave optics, class 12th, and the subtopic is interference of light waves and Young's experiment. So we will continue. We will now discuss interference using light waves. Carefully see. We use two sodium lamp illuminating two pinholes. Okay, and this is the figure. Okay, two lamps, one and two. We will not observe any interference fringe. Okay, fringe. This is because of the fact that the light emitted from ordinary source like sodium lamp, undergoes abrupt phase changes in the time of the order to 10 to the power minus 10 seconds. Thus, the light waves coming out from two independent sources of light will not have any fixed phase relationship and would be incoherent. Okay, so when this happens, as discussed in the previous section, the intensities on the screen will be add up. Okay, is it? So continue. The British physicist Thomas Young used an indigenous technique to lock the phase of the waves emanating from S1 and S2. Yeah, S1 and S2. He made two pinholes, S1 and S2, very close to each other. Listen carefully. He made two pinholes, S1 and S2, very close to each other on an opaque screen. Okay, opaque screen we have seen in figure 10 point. We can see also. Sorry. This is the 10.12 figure A. Okay, this is the figure. Yeah, continue here. So this is the figure I am talking about it. These were illuminated by another pinhole that was in turn lit by a bright source. Okay, light waves spread out from S and fall on both S1 and S2. S1 and S2 that behave like two coherent sources because light waves coming out from S1 and S2 are derived from the same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2. Thus, the two sources S1 and S2 will locked in phase that they will be coherent like two vibrating needle in our water wave example 10.8 we have seen. Okay, the spherical waves emanating from S1 and S2 will produce interference fringes on the screen G dash. Is it? The position of the maximum and minimum intensities can be calculated by using the analysis given in the section 10.4. Okay, so you can see how was looking Thomas Young in their young age. We will continue. we will have constructive interference resulting in a bright region when xd upon d equal to n lambda, that we can say that x is equal to xn n lambda d upon d, where n is equal to integers plus minus 1 plus minus 2, and it will be continue so on. On the other hand, we will have destructive interference resulting in a dark region when xd upon d, okay, where n plus 1 upon m in 1 upon 2 into lambda, that is x is equal to xn n plus 1 upon 2 bracket into lambda d upon d, where n is equal to integers. Okay, you are getting? Thus, very good. This dark and bright bands appear on the screen as shown in figure 10.13. In this figure we can see such bands are called the fringe edge. Okay, these are the called fringe edge. Now equation 10.13 and 10.14 show that dark and the bright fringes are equally spaced, yeah, having equal space. Okay, so next we can see, yeah, computer has generated fringe pattern produced by the two sources S1 and S2 on the screen GG dash. Okay, we have seen the GG dash in the back pages. Correspond to the d is equal to 0.2025 and capital D is equal to 5 centimeter and lambda is equal to 5 into 10 to the power minus 5 centimeter. Adapted from the optics by A. Okay, so next one is, and yeah, this is the book Tata McGraw Hill Publishing. The next one we will see the next subtopic. So thank you for watching.